Okay, hello. I am recording myself giving the talk that I gave in SF a few weeks ago because it wasn't recorded and because some folks would like to see it. So this is a talk about vector search and specifically vector search inside Azure AI Search. So I'm going to start off with describing why we need vector search for RAG and how vectors work and vector databases work, and then really focus in on the Azure AI Search and what it can do for us. So let's start off with my favorite thing, which is Retrieval Augmented Generation, abbreviated as RAG. So I like to say I'm an AI skeptic, but a RAG fangirl. I really, really do love RAG. So what is it? So let's talk about LLMs. An LLM is a large language model like GPT-3.5, GPT-4, or any of the other models like Mistral or Lava. And these large language models are really impressive with what they can do and how much of a grasp they have of language, and not just English language, other languages as well, because they've seen so much language in their training. But they do have limitations. So here, this is where I was chatting with an LLM over a little app I have. And this was just with like GPT-3.5. And what you can see is I said, write a model class using the latest version of Flask SQL Alchemy. Oh, I see. I need to add this to the stage. All right. This is my first time trying to go live. So here in this example, I say, write a model class using the latest version of Flask SQL Alchemy. And it happily responds and says, here's an example of a model class using the latest version. However, it is not the latest version. I know it's not the latest version because I'm a Flask SQL Alchemy maintainer and I helped make the latest version. And this is just out of date. So this is one big limitation of LLMs, is that it has outdated public knowledge. And it also, its knowledge tends to be skewed based on what it's seen the most, right? So if it's seen lots and lots of the old version of something here, then it's more likely to spit that out. It doesn't necessarily know what is latest, right? So either it doesn't have that data at all because of when it was trained, or it just has seen something so rarely that it doesn't think it's the important thing to show. Now, another example here is I could say, do my company perks cover underwater activities? And it says like, well, you should consult your own, employee benefits package, right? You should, check some documentation that's specific to you, because LLMs do not have access to my company perks. They don't know what company I work for. They don't know what those perks are. So it can't answer a question about internal knowledge because it doesn't have internal knowledge. So these are limitations of LLMs. It's also just a feature of LLMs. This is how LLMs work, right? They're large language models. They're very good next word predictors. They've been trained on public knowledge up to a certain point, and they're obviously going to have these things that they can't do. So how can we incorporate domain knowledge with an LLM so that we could get it to answer those questions? There are three main ways that people go about incorporating domain knowledge. The first way is prompt engineering. So for example, with that Flask SQL Alchemy example, if it actually had seen it, I could say, make sure, like in the prompt, I'd be like, make sure you're using Flask SQL Alchemy version 2.14 using SQL Alchemy. Like I could put a lot of effort into that prompt to get it to use the most recent version. And sometimes that works. That can work if it does have that knowledge somewhere, somewhere inside it, and it just needs to be, triggered to use it. But it's only going to work if it's somewhere in its weights, in its training. If it's literally never seen it, it's just not going to work. The next option is fine tuning. And this is where you start with the base model and then you come up with like at least 200, examples of things you want it to know about it or skills you want it to learn. And you do a training with those examples, and you actually end up with a model that has slightly tweaked weights. So this is a fair approach. It is what some people use. We usually caution against this because it's going to be expensive to do the fine tuning. And then it will also be expensive to use a fine-tuned model, at least on Azure infrastructure. Using GPT-3.5 is going to be cheaper than using a fine-tuned GPT-3.5. So generally, we think of this as a last resort just because of those drawbacks. So that leads us to retrieval augmented generation. And that's a way of learning new facts temporarily in order to answer the current question. So it involves retrieving the information and sending that to the LLM so that it can answer the question with that information. So let's see exactly how it is that that works. So in this case here, I'm using a RAG chat app to answer the same questions. And I say, okay, write the model class using the latest version. And we see the latest version, and this is actually correct. And the reason it's correct is because I'm actually giving it the latest documentation. I'm giving it as I ask the question, and so it's able to consult that documentation. And then I can say, oh, do my company perks cover underwater activities? And I give it this document that has the perks, and it can answer that question because it's got that document. So now we're able to, get around the limitations of LLMs by being able to feed sources to an LLM with the user question. So how do we actually do that? So we get the user question, right? And we search some sort of knowledge base, right? So a vector database, Azure AI Search, an in-memory database. We search for the matching documents for this question, right? And we need to use a search that's going to get back a good chunks of information. So we get those back, and in this case, this might be what it looks like. This is text extracted from a PDF. And then we take both the original user question and whatever documents we got back, and we send those to the large language model. And then we get back the answer. So in my experience, this works really well. If you can retrieve the right documents, then large language models are very happy to answer correctly according to those documents. And they're very good at summarizing and synthesizing and all that stuff. So you just need to get that right information and then let the LLM do its magic. So it is all about retrieval. If you can retrieve the right documents, you will generally have a really nice experience with getting your answers correctly. But that means we need to really think about retrieval, and that's what we're talking about today. So how do we do that retrieval, right? How do you do a search? Now, traditional search has been keyword search based, right? But then keyword search has this issue of the vocabulary gap, right? So if I say I'm looking for underwater activities, but that word underwater is nowhere in our knowledge base at all, then a keyword search would never match scuba and snorkeling. So that's why we want to have a vector-based retrieval as well, which can find things by semantic similarity. A vector-based search is going to realize that scuba and snorkeling are semantically similar to underwater and be able to return those. So that's why we're talking about the importance of vector search today. So let's go deep into vectors. It's actually really fun to talk about vectors. So what is a vector, or the longer term would be a vector embedding? So a vector embedding takes some input, like a word or a sentence, or even longer than that, and then it sends it through some embedding model and then gets back a list of floating point numbers. And these numbers, the amount of numbers is going to vary based off of the actual model that you're using. So here I have a table of the most common models. So we have word2vec, and that only takes an input of a single word at a time. And the resulting vectors have a length of 300. And that word2vec has been around for quite a while. So if you've done any sort of work with embeddings before, you might have used word2vec. What we've seen in the last few years is models based off of LLMs, and these can take into much larger inputs, which is really helpful because then we can search on more than just words. So the one that many people have used now is the OpenAI ADA002. That takes text of up to 8,191 tokens, and it produces vectors that are 1536 floating points long. There's also some other ones here. There's quite a few embedding models that are out there that you can use. What you want to look at is, what is it that it can encode? What is it known to be good at encoding? And what are the limitations as well? The important thing is when you're using an embedding model, you need to be consistent with what model you use. So you do want to make sure that if you're encoding your data with a particular model, that's also the model you use later when you're searching. And I see a question from Winston: doing a RAG with PDF documents, if input docs have images and tables, how do you index PDF intermingled with visual data? That's a great question. So you actually see this model here. So these first three models can only encode text. This model here, Azure Computer Vision, can encode image or text. And so that's what we've started using in our RAG app that has experimental support for images. So that's actually what I'd recommend. And I can, point you to the documentation on that. But this, you can pass it image or text and get that encoded. So when we use that in our RAG app, we actually turn the entire PDF page into an image, including the text, because the model is able to look at it that way. I think that's how we do it. So I'd have to double check, but I can point you at that. Okay, so let's take a look at computing a vector. All right, so I have this Jupyter notebook here, and first it just sets up a connection to OpenAI. I'm using Azure OpenAI, of course. I work for Azure, and this whole talk is actually about Azure stuff. So then we have these functions here that are just wrappers for creating embeddings using the ADA 002 model. So we can run that, and that'll just set up the connection. And now we can we can get an embedding. So we're gonna run this here to get embedding for dog. And so we could start with just a single word. And it does take a little bit of time. This is, actually getting sent through the model on the Azure OpenAI servers and getting it back. And you can see all those floating points there. And we can see that it's 1,536. Now we can also put in something a lot longer, like I'm more of a cat person than a dog person, but actually these days I just like humans. Right? So we can write a really long sentence and we can calculate the embedding again. That one was actually a lot faster. So probably just needs some startup time. And once again, we see the dimensions is 1536. So this is an important point. With the ADA 002 model, with all the models, anything you embed, the dimensions that output are always going to be the same. So we have to, a vector to represent dog in the space of the model. And we also can get a vector that represents this whole long sentence. And when we're indexing documents for RAG chat apps, we're often going to be calculating embeddings for like entire paragraphs, like up to like 512 tokens is best practice. So we're actually going to be calculating embeddings for decently long things. Now, you don't want to calculate the embedding for like an entire, book, like War and Peace. First of all, because that's above the limit of, 8192 tokens, but also because the more that you try to calculate embedding for something, like the more things that are in there, the more nuance is going to be lost when you're trying to compare one vector to another vector. So we want to have like the, optimal chunk size, which is usually actually around, for input wise, like optimal size to embed is about 512 tokens. And in English, you could think of tokens as a word, but it doesn't directly map. All right, so we've calculated an embedding. And now the question is, why are we even doing all this? Why are we calculating embeddings? Why do we have these, lists of floating point numbers? The whole point of calculating embeddings is so that we can calculate similarity between vectors, so that we can see, oh, this vector is similar to another vector. This new vector is similar to this other vector in our, vector database. So the way to calculate similarities is to use a distance measurement. The one that we're going to use is cosine similarity. This is the recommended one to use for the ADA 002 model. There are other ways of measuring distance, and some of them might be more appropriate for other models. But for ADA, we are going to use cosine similarity. And this is, roughly how you calculate that. It's the dot product over the product of the magnitudes. And what this does is it tells us how similar two vectors are. Like, what is the angle between these two vectors in multi-dimensional space? So here I'm visualizing in two-dimensional space because I can't visualize 1,536 dimensions. But you see the idea here is that, okay, if the vectors are really close, then there's a very small theta, and that means, your angle theta is near 0. That means cosine of the angle is near 1. So if you see 1, then that's the same vector, and anything near 1 is a very close vector. Now, as as the vectors get farther and farther away, then your cosine goes down to 0 and potentially even to -1. So let's try actually doing some similarity comparisons, right? So here I've got a function to calculate the cosine similarity, and I'm using NumPy to do the math for me, since that'll be nice and efficient. And now I've got 3 sentences that are all the same, and then these sentences which are different. And I'm going to get the embeddings for each of these sets of sentences and then just compare them to each other. So I'll go ahead and get the embeddings. And one thing I wanted to point out is that you can get batch embeddings, and that's a helpful thing. So this function will actually batch up the embeddings. So we are doing just 2 calls instead of 6 calls. So that's a very common thing to do when you're computing embeddings with the API, is to batch them up. Okay, so what we see is that when the 2 sentences are exactly the same, then we see a cosine similarity of 1. That's what we expect. And then when a sentence is very similar, then we see a cosine similarity of 0.91. And then this sentence here is 0.75. Now, when you look at this, it's hard to think about whether, like, does 0.75 mean this is actually pretty similar, or does it actually mean it's pretty dissimilar? So I did a little exploration of this. So let me show you the little website I did here. Let's just look at the word dog. And I actually did this comparison across both OpenAI and Word2Vec. So this is just 1,000 words, and I calculated the embedding vectors for each of these words. And I did it in both Word2Vec and OpenAI. So we can see, like, dog is the most similar to God in this, in this set of 1,000 words. And it has a 0.866 similarity. And then if we look at least similar, we see 0.74, which is ISN, like part of isn't. 0.74 is the least similar one in this set. So in a set of 1,000 words, the range of similarities between 0.74 and 0.86. And I made this similarity histogram here so you could see that. Whereas if you look at Word2Vec, it's between 0.76 for cat and then all the way down to like negative 0.05. So that is more what I was expecting when I went into this, because, when you look at that cosine graph, you think like, well, cosine can go from -1 to 1, then, why aren't our similarities going from -1 to 1? So what you see when you do similarity with the ADA 002 model is that there's generally this very tight range between about, I think 0.65 is the lowest I've ever seen. And then, we got like a 0.91 here, which is actually one of the highest I've seen, right? So this 0.75 is actually really, really dissimilar. And I can prove it by doing, let me just put like absolute nonsense in there, right? So here we can see that one got basically the same score, 0.74, right? So this is actually in the land of OpenAI vectors, it's actually very dissimilar. So usually when you're looking at vector similarity, you're not looking necessarily at the absolutes, you're looking at relative, right? So this one is definitely more similar than this one, right? It's hard to look at it, these low ones, and know exactly how dissimilar they are. So you really want to be looking at the relative differences because they are in such this like tight space. And I looked into this when I discovered this because I was like, why are they in such a tight space? And it's apparently just because of the particular training process, and where they have this pooling layer, which ends up skewing all of the vectors in a similar direction. So if you can kind of visualize in your head, like imagine this cone, this kind of 3-dimensional, ice cream cone, where all the vectors are in that space, which means they're not getting all the way to here. They're staying within this ice cream cone of the space. So I thought that was really interesting, and maybe can give you a little bit of intuition when you're looking at cosine similarity scores for the ADA 002 model. And as you see, it definitely does vary, vary between sets. I also did this with movie titles because I just thought it was fun. So, we have like Disney movie titles, right? So we could go like, The Many Adventures of Winnie the Pooh. So I calculated the vector embeddings for all of these titles, just the titles, nothing else about the movie, just the titles. So we see most similar is Winnie the Pooh, and that makes sense. But then the third most similar is the adventures of Huck Finn. So that's another observation I had with OpenAI, is that there tends to be, in the encoding, it's definitely considering not just semantics, but also similar spelling. And we saw that with this one, because the most similar, word to dog is God. And arguably, we would have thought it was cat, right? That's what we have in word to vec, which is purely semantic. So in the OpenAI similarity space, it's whatever it's in its latent space, but we see both similarity in terms of semantics, but also in terms of like syntax and grammar and how things are used. So here we've got, the adventures of Huck Finn, adventures in babysitting. So we see both things that are, semantically similar, but also spelling similar. And then we can look at the least similar. And once again, for the least similar, we're seeing 0.71 is the least similar score. So really similar range in terms of these cosine similarity scores. Okay, so vector similarity. So now the next step is to be able to do a vector search, because everything I just showed you was similarity within the existing data set. What we want to be able to do is be able to search for arbitrary things. And so what we do is we take a user query, right? Whatever they're trying to look for, we compute the embedding vector for that query using the same model that we did our embeddings with for the knowledge base. And then we look in our vector database and we find the k closest vectors for that user query vector. And we can either do a comprehensive search or an approximation search. And then we return those k closest vectors. So let's take a look at how we could do that in code. So here, we're going to do a vector search on that movies data that I showed before. So we're just going to load it in as a JSON. So I've already computed all the embeddings for the movie titles. We load that in, and now I can actually do a search. So I've got my query, which is my neighbor Totoro, because those movies were only Disney movies. And as far as I know, Totoro is not a Disney movie. It's a Miyazaki movie, or Studio Ghibli is the studio. So then we're going to go through, and for every single, we're going to do a comprehensive search here. So for every single movie in those vectors, we're going to calculate the cosine similarity between the query vector and the vector for that movie. And then we're going to create a data frame and sort it so that we can see the most similar ones. So let's take a look. Okay, so for Totoro, it thinks the most similar one is Toy Story, but it also has Send to Chihiro, which is Spirited Away, which is actually a Studio Ghibli movie. So what I realized after doing this search is that Disney became a distributor for some of the Miyazaki movies. So we actually see Ponyo and Spirited Away show up in this list. So it's interesting. And most of these stories are about like large toys or, toys brought to life, animals brought to life. So they do feel fairly similar to Totoro. And this is purely based off the title, but remember, this is the ADA002 model, and it's seen so much of the world. So in its embeddings, there's more than, there's just so much in those embeddings that we'll never really understand. But we get really interesting responses even by just embedding the title. Now, if I was actually going to make a search engine for finding recommended related movies, I would also be embedding the descriptions of the movies, at least, right? Like a paragraph describing, and that would get, I think, much better recommendations versus going just off the title. And this is, so as you say, this is doing a comprehensive search, so it's searching the entire space. And I was able to do this because I only have 500 movies here, so it was able to do this pretty quickly. But as you grow to have a database that has many more vectors in that, you're going to have to use an approximation search. And so we'll talk about options for that. All right. So moving on to how do we store our vectors? So we're going to want to store in some sort of database, usually a vector database or a database that has a vector extension. We need something that can store vectors and ideally knows how to index vectors really well. So here, this is just a little example of Postgres code using the PG vector extension, which is a popular approach that some folks use, especially if you're already using Postgres. So here we, declare our vector field, our vector column, and we say it's going to be a vector with 1536 dimensions, and then we can insert our vectors in there, and then we could do a select where we're checking to see which embedding is closest to some new embedding that we're interested in. And we also need to do an index. So we actually should do the index before the select so that we have an efficient way of searching. So this is an index using HNS-W, which is an approximation algorithm, which we'll talk about. So this is the kind of thing you're looking for in a database, is the ability to say, hey, this particular field is a vector field. I want to make an efficient index for that field, and I need to be able to query it. And I also want to be able to combine queries with other queries, with access control, all that sort of thing. So on Azure, we have several options for vector databases. So you could, if you already have your data in a database, like in Cosmos DB, we do have vector support in the MongoDB vCore and also in the Cosmos DB for Postgres. So that's a way you could keep your data where it is. Like, for example, if you're doing a RAG chat application on your product inventory, and your product inventory, changes all the time and it's already in the Cosmos DB, well, then it makes sense to take advantage of the vector capabilities there. Otherwise, we have Azure AI Search, and this is a dedicated search technology that does not just vector search, but also keyword search, and has a lot more features. So, and it can index things from many, many sources. So this is what we generally recommend for just really good search quality. And this is what I'm going to be showing for the rest of this talk. And we're going to be talking about all its features, how it integrates, and what makes it a really good retrieval system. Because I was saying, when we're doing RAG, we want really, really good retrieval. All right, so let's talk about each of these features here. So we're going to go into more detail. So first of all, Azure AI Search does now have vector search. It actually didn't as of a year ago, but if they realized how important it was to add vector search and added it to there. And so you can use it via, the Azure Python SDK, which is what I'm going to use it with, but also with semantic kernel, LangChain, Llama Index, any, those packages that you're using. Lots of them do have support for using Azure AI Search as the, the RAG knowledge base. So let's take a look at how to actually use the SDK to do a vector search. So I'm going to start with my setup. And this is just, grabbing from the Azure Documents, Search Documents package. And we create a search service. And we also are creating our OpenAI client. Okay, so everything's set up. Everything's credentialed. Now we can actually create an index. So I make so many of these indexes. Here we go. So this is a teeny tiny index that we're making. And it just has a couple fields. So we have an ID field, and that's like our primary key. And then we have the embedding field, and that is going to be a vector. And we tell it how many dimensions it's going to have. And then we also give it a profile. This is embedding profile. And then down here is where we describe that profile. So we say this embedding profile is going to use this algorithm configuration. So this is where we describe what sort of algorithm or indexing strategy we want to use. And we're going to be using HNS-W. HNS-W stands for hierarchical navigable small world. There we go. And it is pretty much like the go-to for doing vector searches these days. There's are a couple other options like IVF and some others, but those are the two big ones. So most folks these days are using HNS-W. This is what Azure AI Search supports because it works really well, and they're able to do it efficiently at scale. So we're going to say it's HNS-W, and we can tell it like what metric to use for the similarity calculations. We can also customize other HNS-W parameters. If you're familiar with that algorithm, you can pass in some more. So we set it all up. So this is like telling it, what kind of index it's going to use. And let's run this here. Okay, so it has created that index. And now we just are going to upload these very simple documents, right? And you can just see they each have, just 3-dimensional vectors. So it's just 3 documents that each has a 3-dimensional vector. So that is now in the index. And now we can do a search. So the way we do a search is we're going to say, okay, we're not doing any sort of text search. We're only doing a vector query search. So we say, here's a vectorized query. This is going to be the query vector 1, 2, 1. We're asking for the 3 nearest neighbors, and we're telling to search the embedding field, because you could actually have multiple vector fields. So then we do this search and we can output the score. Now the score in this case is not necessarily the cosine similarity, because score can consider other things as well. And there's some documentation about what score means in different situations. But we do, what matters is what's relative, right? So we can see what's at the top. So this one, it thinks that this one is the most similar. And then it goes down. Now, if we put in like a really different vector, like this, then we can see much lower scores, right? So it's about, I usually don't look at the absolute scores myself. You can, but I usually look at the relative scores. So that was an example with just a small index. And now what I want to show is doing it on a real index. And I'll actually show you that index in my portal. So let's find that index in the portal. Let's go to the portal here. All right, there it is. That's the search service. And then I can click on indexes and click on this index. So it has 691 documents, where each of these documents is actually a chunk of a PDF because of how we index them. And then we can, here I'm just searching for everything just to show you what is in this index. So we can see ID, content, this is the text content, embedding is the vector embedding. And then we can see what the page number was from and the file name as well. So this is what we're going to be searching. So let's go back here. And so here we're going to take that learning about underwater activities query and compute that into an embedding. And then we're going to search using a vector query. So we're not searching text at all. See this first thing here, the none. This corresponds to search text. So we are not passing in this search query here. We are only passing in the vector query. So we've turned this into a vector. We're passing that in. We told it to get 50 nearest neighbors, and then we can show them here. 50 is actually quite a lot. Normally I would do less than that. Normally I would do like 5. I'll change that. Okay. And so here we can see it got back results, and we can see the very top result has scuba diving lessons, skiing, and snowboarding. So this is what we are looking for. And this is exactly what we can get with vector search that would not have worked with a keyword search, because a keyword search wouldn't have found underwater anywhere in here. All right, so that's a vector search in the Azure AI Search SDK. And as you saw, we did use an approximation search. So we did the HNSW. An HNSW is a specific example of an approximate nearest neighbors search. So you'll also hear this term ANN. And so HNSW is a specific instance of that. There are other ones I said, like IVF. So this one, HNSW has very good performance recall, and it does have additional parameters that you can tweak if you find that you need different performance out of it. You can also do an exhaustive KNN search, and that just means it's going to go through the entire set of vectors and find all the nearest neighbors. Typically, this is not recommended because it can take so long to do this, to have to go through and check out, and compare every single one. However, there might be some scenarios where you want to do it. It can be useful if you're trying to recall, make your baseline. So if you're trying to evaluate how well HNSW is working, you can first run a KNN search for some examples, and then compare that to the results of HNSW and see, are you getting back the same results or good enough results? You could also Use exhaustive KNN search if you are in scenarios where you have highly selective filters. So if there's some pre-filter, like, getting just the documents for a user, and you think that gets it down to a reasonable level, like only 1,000 documents, 10,000, whatever, then that might be a situation where you could just say like, well, we can go ahead and do an exhaustive search. So it is certainly an option, and you just want to keep think carefully about how many documents you have, what sort of performance you need, and just do some, looks, look at the quality of your results to see how it's working for you. Now we have other capabilities when we're doing vector queries. So we can, we can combine our vector filters with other filters. So, anything that we could already do with Azure AI Search. So if we need to filter by some column, if we need to do, less than, less than some time, greater than some time, we can still do all of those in combination with a vector query. Now, one thing you have to keep in mind is whether you should be doing a pre-filter or post-filter. You generally want to almost always want to do a pre-filter. And this means that you're first doing this filter and then doing the vector search. And the reason you want this is because think about it. If you did a post filter, right? Like, so imagine you're doing something, like this tag perks. So if you first do the vector search to get all the related documents, and then you apply this filter here, then you just might end up not finding anything at all, because maybe it didn't find anything, in its top 10 results that had tag equals to perks. So instead, you want to do the you want to do the filter, this filter this filter here first, find all those documents that qualify, and then pass that to the vector search. So just think carefully about that. It does default to pre-filter, meaning it's going to run this filter first and then do the vector search, but you do have the option for post-filter if you need it. We also support being able to do multi-vector scenarios. So for example, you could have an embedding for the title of a document that was different from the embedding for the body of the document. And you can search these separately. You could, search these at the same time with different things. So you have different options because you always specify what you're, running a particular query against. The other time we use this a lot is if we're doing multimodal queries. So if we have both an image embedding and a text embedding, we might want to search both of those embeddings. And we'll see that when we do the image search. All right, so lots of options there. And of course, this being an Azure product, we've got data encryption, we've got secure authentication, we've got the ability to put in a private endpoint, we've got all this compliance certification. So everything that comes with being an Azure product. Now, this is really, really exciting, is that we can now do searches on more than just text, right? So 8002 was just for text, but we have at Azure Computer Vision SDK has a multimodal embeddings API that can turn images and sentences into an embedding in this space that understands both images and text together. And it's just incredibly, incredibly cool and powerful. So let's go ahead and see what that looks like in code. So let's go here. Okay. All right. So first we have setup. So once again, we're going to connect to a search service, and then we create a search index for images. So this one has ID, file name, and embedding. This time, the vector search dimensions is 1024 because that is the dimensions of the embeddings that come from the computer vision model. So it's a slightly different length than the other one. And we're going to do everything else the same with HNSW and create that index. Now, I already made that index and populated it, so I'm just going to not run that. Now we're going to configure the computer vision SDK. So we're just doing HTTP calls to it. Sending in our authentication information, and I've made a function that can get an image embedding based off of an actual file, a binary file, and also made a function that can get a text embedding based off of a string of text. Okay, and so then we can use that function in order to go through all these local images I have here, and these are actually pictures from an old Etsy shop I had back when I lived in the woods. and I collected all this driftwood because we were near a beach, and I was trying to figure out what to do with this driftwood. So I passed all of these into into that computer vision SDK in order to get an embedding for the image. And then I upload them to Azure AI Search with the ID, file name, and then their embedding. All right, so I did that, and I'm not going to do it again just because it takes a little bit of time. And now that that is ready, now I can query it using new images. So I have another folder which has separate images which have not been added to the index. So we can query those using this folder. So let's see, like this is the one I have here. So T-lights inside. Okay, so this is what this looks like. So we can take a look. Okay, that's what it looks like. Now we convert that into an image embedding and we do a search, and we're only searching on the embedding field, not on the file name. And so that's going to do the vector search on that embedding. And you'll see what it gets back as the top result is in fact the same product, but in nighttime lighting. So it was able to see that these two images were very similar. And you might think like, oh, it's just the file name, but we didn't actually give it the file name at all. It was just it seeing that the images were really similar. And here's the cool thing is that then we can also do, we can do text embeddings to search image embeddings. And this is what really blows my mind. So we could do like, see candle. I don't know, we'll try it. All right. And then when we open it, it gets that a sea candle. So it thinks that this is the most similar image to sea candle. We could do this in different languages. So that would be like, let's see if that's gonna work in Spanish. Vela del Mar, I think. And yeah, it got it. So remember, like these are LLMs, they understand more than just English because they've seen quite a lot. We could do, let's do Spanish for earrings to make sure that it's getting other things. Yeah, so it found earrings. And now I want to show you the thing that really blew my mind is if I pass in Lion King, what it gets back is this driftwood burning of Hakuna Matata. And this to me is so impressive because that means that the model could see the word Hakuna Matata that I, scratched onto this thing, and then knows, like extracted that word somehow in his space, and then also knows that Hakuna Matata is related to Lion King and gave back this image. So it's just incredibly, incredibly powerful. And it's a really impressive model. So it's been pretty fun to play with. So we do have support for it in our RAG chat repo. So that's this one, this is the chat application. I should show this GitHub here. So it's just on this GitHub repo, and there is a document specifically about how to try out the GPT-4. So if you're interested in trying GPT-4 Turbo with Vision, so this is using both the Vision SDK that I just showed and also the GPT-4 Turbo with Vision in order to answer questions about images. And I have an example here where I asked it to identify a correlation between oil prices and stock market trends. And we can look to see what here, this is basically what we ended up finding. So we found both text and we found image embeddings, and we sent all of this to GPT-4 Turbo with Vision. So to answer that, question from Winston from the beginning, this is the sort of thing you could do if you have PDFs that do have a lot of images, is that you could consider using this sort of approach to compute embeddings for the images themselves. And then, but then you do have to pass them to GPT-4 Turbo with Vision because it's the only model that understands images. It's pretty cool. It's definitely experimental in our repo. I don't know anyone who's actually doing this particular thing in production with the images. It's definitely a little bit slower. We have some ideas for speeding it up and in terms of like how we can be more efficient with what we send. But it's really, really interesting to see what it can do. Okay, so let's talk more about retrieval again and relevance. So when we really want to get the most relevant chunks of information for our RAG app because we want to make sure when we're sending information to an LLM that we're sending just the right amount of good information. So if we look at here, and we can look at here and actually see this is what we're sending to the LLM. So we are not sending entire documents. We're not sending all of our documents. We're sending chunks from a document, and we're sending just the chunks that we think will answer a question. And in this example, I think we're doing 3. Yeah, we're doing 3. We could maybe up that to 5, but you don't want to send too much information. And the reason for this, there's this paper called Lost in the Middle. And what they found is that if they sent too much information to a model, even if it, technically could fit that amount of information in its context window, eventually the model would stop paying attention to things that were in the middle of the information, and things would get lost. So if you sent too much information, you get a degrade in answer quality because it would just stop paying attention to it. So we really want to get just the right amount of information. And the right amount is usually between 3 to 5 chunks of information, where each of those chunks are about 512 tokens. So that, according to research, is the right size of information to send to an LLM so that it can really answer things the best. So we figured that out, but we also, so how do we get, if we're only going to get 3 to 5 results, how do we make sure that those 3 to 5 results contain the most important information, right? So what we do is we use every possible trick in the book, and that's what Azure AI Search does. So it does vector search, it does keyword search, and then it can combine the results from the vector and the keyword search using this fusion step. And then it also has an additional machine learning model called the semantic ranker that can take those combined results and then really rank within those so that the very best things are at the top. And then you can just say, all right, I just want the top 5 from theirs. So that's what we see, is that this is how you get the optimal relevance so that you can have those top 3 to 5 be absolutely the best results, is by using all these options together. So I'm going to demonstrate that in code, as always, because that's what will convince you. So here we go. We have the setup again. So setting up all the clients and authentication. All right. Now, we're going to first look at a situation where vector search, because you might think like, oh, why can't I just use vector search? Well, vector search does not work for all queries. And there's actually quite a few queries where it's not going to work. And the classic example is exact strings. If somebody is looking for something that's an exact string. So here I'm searching for the string $45. Maybe I remembered something costs $45. And so I'm looking for that. So I'm doing a vector search, passing in the vector for $45 and trying to find back results. And, it does get back vectors. Here's the thing about vector search. Vector search will always get you back vectors, because something is, as long as the space has more than one vector, then it'll just find whatever's closest, even if it's very, very far away. So it does get back some, documents, but those documents do not have the string $45 in it. So it basically didn't find what I was looking for. Now, if I do a text search, that was really fast. I immediately find the matching text, right? So this is what I was looking for, was this exact string, $45. So here you can see vector search failed, keyword search succeeded. Okay, so then can we do hybrid? Yes. What we do is we specify both the text query and the vector query. And then Azure AI Search will do the merging of them with that reciprocal rank fusion step. And here we can see that $45 is at the very top here. So that's great. So it was able to figure out which of those responses was best. Now, the thing is that hybrid ranking alone is not always optimal. So here we're doing that underwater activities query that we saw earlier, and I'm doing, search query and vectors query. So that's a hybrid search, and I do this search. And what I see is that, skiing and snowboarding is here, but it's number 3. And that would have been good enough for the LLM, but ideally it would be number 1, right? We're kind of risking this falling off. So how do we get this to be number 1? So what we do is that we use the semantic ranker, and these are the options to enable a semantic ranker. And so by doing the semantic ranker, That's an additional machine learning model that's based off the Bing model. So Bing uses it for re-ranking in its search results. So it's good at re-ranking. And it runs after the hybrid search results come back and are fused together and tries to do, some additional re-ranking. And what you can see is that it did indeed bring snowboarding and scuba diving to the very top of the list. So in conclusion, that is why we want them all. We want to do a vector search, a keyword search, hybrid search of both of those, and then use that semantic ranker on top in order to get the optimal ranking of the candidates so that we can say, all right, we're just going to take the top 3 and give those to the LLM, and that should contain our results. So semantic ranker. Now, the thing about semantic ranker is that it does actually cost additional money. So that might be the reason for some folks why you might decide it's not worth it to use it. We're hoping to bring those costs down, but you can try it out for free for the first 1,000 requests to see how it affects your answers. And so they did some research in this really good blog post that I recommend everybody read. About they looked at all these different metrics and comparisons to see what created the optimal search. And they also, this is where I got that 512 size. So they try to figure out what was the optimal size of tokens in chunks, and where do you break your chunks up, and what kind of overlap should you have between chunks. So they did a lot of really cool research about how to properly prepare your data for a RAG, and then how to search that data. And what they found was across the board that generally hybrid plus semantic does get the best results. So we can see that in this chart here with hybrid plus re-ranking getting the best results overall. There's also this other chart which breaks it up into different query types. And this is really interesting because you can see there's definitely areas where it's particularly stronger. And areas where some of them are particularly weak. And this is something really interesting to think about in terms of your particular use case. Like, what kind of queries are your users issuing, and what's going to work? And also, what does your documents look like? Do they have lots of exact strings? What's going to work best for your particular situation? Where does it fit in this table? All right, so now we can talk a little bit about data ingestion. So I've talked about this briefly before, but you need to think about how you're going to ingest data into your knowledge base, in this case into Azure AI Search. And so ingesting data means you have to extract the data from your document in some way, and then you need to chunk up that data into good sizes for an LLM, if assuming that your data is sufficiently long, right? Because they're saying the optimal size is about 512 tokens. You can think of that as about 500 words. So if your data is significantly longer than that, like you're indexing, 50-page documents, you're definitely going to want to chunk those up. So you want to chunk those up. You need to chunk those up with an overlap so that there is actually overlap between each of the chunks, and that helps with the LLM understanding. And you need to think about where you're going to cut things off, right? You don't want to cut things in the middle of a sentence or in the middle of a table. You want to, preserve whole tables across it. So there's a lot of effort that goes into figuring out how to chunk. And there's various libraries that help with that too. So Llama Index has a lot of great functionality in it for doing this. LangChain probably does as well. A lot of people have written their own. We've got our own chunker in our repo. There's probably the thousands of chunking scripts out there now. And there's also, we're now having chunking as a service, I like to think of it. It's called integrated vectorization. This is integrated into Azure AI Search. So you can actually have this all done in the cloud. So you just say like, okay, point at this blob storage, and it can crack a bunch of formats. So if you've got PDF or Office documents or whatever, it's going to crack those documents open, extract the text, chunk those texts into passages based on all these best practices, based on research, and then compute the vector embeddings for each of those, each of those chunks, and then store them in AI Search. So this is now getting offered as a cloud service, so that you don't have to be, writing this chunking code yourself, running all this data ingestion on your machine. You can hook up to some storage, and all of this will happen for you. So this is really nice, so that we don't all have to write our own chunkers. There's also integration for Azure AI Search in the new Azure AI Studio and also in the Azure AI CLI. So check that out if you want the more, if you like the WYSIWYG approach to doing things or if you like the CLI approach to doing things, there's some integration there. And here I just wanted to, talk a few more use cases for RAG. I've seen lots of customers using our particular RAG chat app repo, which is the one I had open here. So we've got lots of customers using this for all kinds of really cool, interesting use cases and actually putting this into production. So we've seen people use it for public government data. So that's great because public governments have so many PDFs, and imagine being able to actually search through your local government data. I've actually process my own local government data just for fun. So, that's a definitely use case. Internal HR documents is a huge use case because everyone's got these internal documents that are hard to sift through. Customer support request, anything to help customers, inventory, common questions, all that sort of thing. Really, really commonly seen that. Technical documentation, issue trackers, product manuals, all of these can be really great things to feed into a search index and do a RAG chat on. So for next steps, here are some links where you can learn more about Azure AI Search. You can read that amazing blog post that talks about how to optimize your ingestion and your search. You can go ahead and use our repo to deploy a RAG chat for your organization's data. You could explore Azure AI Studio. You could join us for next week's Microsoft AI Chat App Hack from January 29th to February 12th, where we're going to be building on this repo, and we're going to have tons of sessions to go into more detail about how to make a RAG chat app using Azure AI Search. So there you go. And you can, check out the slides, check out the links, and I hope that was helpful. Oh, I see questions. Cool. Let's see. So how well does vector search work on complex topics? Oh, let me try. Can I show? Okay. How does it work on complex topics like when a lot of contextual background information is required? Is it 3 to 5 search results limiting? So I haven't seen it be limiting yet, but that's why we do have that as an options, like in our, for this one here, developer settings, right? Like this is like a numeric option. So we could retrieve a lot more. And if we were seeing that it just wasn't getting the results. So I have in the documentation here, I talk about the process of, debugging the quality. So customization, so improving answer quality, right? So we have to identify the problem point, right? So is it that we're not getting good search result for the query or that we're not getting good answer based on the search results? So that's what I always recommend is that, when you're doing debugging a RAG chat app, and if you're not liking the answers you're getting, first we look and see okay, what did we actually pass into the LLM, right? Is our answer in here? Because a lot of times what we find is that the answer isn't in here. Almost all of the situations I've helped customers with, we just found that the answer wasn't in here. And that was because of something around their search configuration or the way they ingested it. So that's what I would look at first. There definitely could be situations where you're going to need to grab more than 3, 5, 10, etc. Or maybe you have to do smaller chunks. I also did, I did a sample RAG on diabetes research papers, and actually seemed like it did pretty good on that too. But it's a great question. And that's why I encourage people to try these things out and then document it, because RAG it's really new. I've only been doing this for, 6 months. And so I think we're all learning about best practices. So if there is some particular situation, then you do some experimentation. It's really helpful if you can document that. And so, yeah, you're saying there's a law case where XYZ important facts need to be factored into a response. Is vector search RAG alone appropriate? So you can also think about doing, doing other things as well. Like if maybe you need to search for supporting facts or search for relevant law things. I was actually just talking with my colleague about this today, so I should have this open. Function calling. So OpenAI, the SDK or the APIs has this notion of function calling or tools where you tell you tell the API what potential functions it could call. And so if it realizes like kind of it has to detect that it needs to call those additional functions, but you can use an LLM to make a decision about what path it's going to go down. So if you find that doing just a search isn't working in all situations, sometimes the approach could be to have its, pick between doing the search or getting background facts or something, right? It's really going to depend on the specific scenario, but this is something to think about as well. Is like, yeah, there's definitely lots of situations where just doing a straight up search may not be what you want in order to answer a question. And then you have to figure out how you're going to like chain together the process of answering the question. And I think if you look at LangChain, you'll see there's lots of like ideas about different ways of chaining together processes. We did use some of those LangChain techniques and agents, and then ended up simplifying and going away from them. But I think there's lots of ideas there about other approaches, and I also would recommend looking into function calling and considering whether that sort of thing might help you out. But the first thing to do is just to see how it works, and then start debugging and looking and seeing where the problem points are, and then trying stuff out and seeing what works and then documenting it. Cool. Well, thank you for the questions. This is actually the first time I've actually used StreamYard just on my own. But I wanted to get this talk recorded for other folks who wanted to see it. And yeah, so thank you. Oh, wow. And multiple people are actually here. Yeah. Oh, there's people watching. That's great. Okay, so we had another question. Is it possible to add a logger and log each step of the process? So this is actually what we do here in the thought process tab. And you can also see, if you like another approach is you could use prompt flow. Prompt flow is an Azure tool. I don't have my prompt flow open right now, but it's an idea of doing a directed acyclic graph in order to describe I'm trying to see if I can get a picture of it. Yeah. So you can actually like describe your whole RAG process. So if you work well with like graphs and WYSIWYG and that sort of thing, you might like prompt flow. It's in the Azure AI Studio. And that visualizes that way. What we do for our, for this particular application is that we basically do log in our own little dict, in the Python code, what each of the steps are. So the steps here is that first we get the user query, and then we do this step here where we do an initial chat completion call in order to turn the user query into a nice keyword search. This is not something you need to do for a RAG. You could skip this step, but we like to do this because it tends to get better search results. Because users tend to have spelling mistakes and put in fluff words and stuff like this. So this is going to generate a nice clean keyword search that we can then pass into Azure AI Search. So we take that nice clean search and we pass it into Azure AI Search. And these are the search documents we get back, the search chunks, the chunks from the documents. And then we have the prompt. This is the actual thing we send to the API. I have the vision tab open right now, so you can actually see where it sends images. Normally we're not sending images. So here we can look at this one here. So we get back the search results, and then this is the full message that we send to the API. So we can see the system message, we can see the question, and then the attached sources here. And then we get back the response, which we can see there. So this is a form of logging. It's, it's covering the big steps of our RAG approach here. You can also, of course, our code is Python code, so you can add additional logging if you need it. But really, like, this covers the core things, because if you're going to have quality issues, it's going to be at one of these points, right? It's like, well, did this get generated weird? Did you get back good results? And what did it look like when you finally sent it to the LLM? Great question. And thank you, Spencer. Cool. Okay, well, I will end this stream now. But if you do have additional questions, you can And I guess you could put them in the comments of the video. You can also try out this repo here. You can come to the hackathon next week. And yeah, thank you for joining.